Hello and welcome back. If you follow the channel, you know that we are trying to replicate the famous Haffler and Keating experiment that directly measured time dilation as predicted by Einstein's theory of relativity by flying 4 HP 5061A atomic clocks around the world in 1971. We pick up from the previous episode where we tried to establish a baseline by comparing two atomic clocks at rest. Sadly, that didn't go as planned, with the two clocks drifting more than the relativistic time shift we'd be trying to measure. I strongly suspect that one of the clocks, which we already had to bring back from the dead with a heroic repair, is the culprit. We'll eventually come back to that one, but for now, I want to move on to the next clock, which, you guessed it, is also broken. Let's see if we can revive it and get better results. This might seem silly, but the measurement is so close to the stability limit of these clocks that we'll need as many as we can repair. Remember that the original experiment used 4 of them for that very reason. Hello, I'm back with my atomic clocks, and one is upside down. That's the one I repaired, and the reason it's upside down is because I don't like it. I had not so good stability results between the two clocks, and I know that Marcel had another good clock with a good tube, and I asked him to bring it so I could replace it, but he brought me two. He brought me the good one that's down there somewhere, then he brought me one I didn't know he had that doesn't work but seems to have a very new tube. It's a square one by says Datum Inc., but I think it's HP. It's the HP cesium tube that went to Datum, then FTS, then Symmetricon, then Microsemi. It has changed hands a million times and still make this a similar tube. Interesting enough, it won't lock. See, the green light is not coming on. However, in terms of beam current, I have tons of beam signal. I had tons of second harmonic. When we got it, it was actually off scale, so somebody wasn't able to lock it, and I think that one got tossed. But if I look at the signal from the tube, there's actually a way to look at it directly, and that's what I have done here. They give you 2 test ports. There is one on the amplifier A7, basically the amplified signal out of the tube, and out of J2A8 comes the reference signal. So it's open loop right now. So I'm going to wander off the peak, and I'm on one side of the peak, and on the other side of the peak. Alright, we are barely 3 minutes in, and it's already time for the elevator music. This atomic clock is very intimidating in its complexity, but if you break it down into functional subsystems, it is somewhat approachable. Today we'll be looking at the electronics that lock its microwave frequency to the peak of the cesium tube. We'll skip over the quantum physics magic that happens within the tube, which I have explained in a previous brain-numbing episode, link in the doodly-doo. But the result of all that magic is that when we input a microwave frequency close to 9.192631770 GHz into the tube, we observe a sharp peak in the output current versus frequency curve. The point is then to tune the microwave frequency to the very top of the cesium resonance peak, at which time will be exactly at 9.192631770 GHz, which is the atomic definition of the second. This frequency is then divided by the rest of the instrument to provide a convenient, ultra-stable 5 MHz output. But back to our main point, how do we know that we are right on top of the peak? Let's look at the blown up section of the peak. Instead of probing the peak with a static frequency, the instrument constantly moves the frequency a tiny bit around its center to sense where it is in relation to the peak. In order to do that, a phase modulation signal at 137 Hz is added to the microwave generation chain. This produces a frequency wobble around the mean value. Let's assume we are on the left side of the peak. When the frequency lowers, we shift away from the peak and get less signal. But when the wobble brings us closer to the peak, we'll get more signal. The result is a 137 Hz tone superimposed to the output of the tube in phase with our frequency wobble. If we were on the other side of the peak, we'd see a similar effect, but now we'll gain signal during the lower frequency excursion. We'll still have a 137 Hz tone, but with opposite phase. When we are perfectly centered at the peak, we'll see a small decrease on either side. A new tone appears at double the wobble frequency, the so-called second harmonic. Meanwhile, the fundamental tone at 137 Hz has disappeared completely. This condition, lots of second harmonic and no first harmonic, indicates that we are locked to the cesium peak and lights the green indicator. Most of the time we'll be in an intermediate position, sampling both the peak side and part of the top, so we'll have a mixture of the fundamental and the second harmonic. The amplifier at the output of the tube has strong filters and separates both harmonics for us. You should now be able to figure out what I have on the scope. The yellow triangle wave is the 137 Hz phase modulation signal that creates the wobble. The green signal is the tube output filtered for the first harmonic, taken straight out of the amplifier. If I tune the instrument manually and see the first harmonic disappear and invert its phase as I cross the peak, our precious cesium tube is probably functioning properly. This would be a great relief. The fault is probably elsewhere in the electronics and potentially repairable. So basically, that's a beautiful demonstration of how the peak is measured. There is a 137 Hz modulation that moves the frequency around just a little bit. And if you're on one side of the peak, you are in phase, and if you're on the other side of the peak, you're out of phase. If you're right at the peak, you're at the top, right? And you hardly see any variation when you're there. And actually, when I'm there, this alarm lamp goes off because it sees second harmonic. And if I go a little off, it should come back. There you go. Right, it won't, I'm too far off. This tube has excellent signal, but it won't lock. And then if you look at the control signal, which is the one that's supposed to take a cue of this in or out of phase signal that we see here and bring it right in the middle, it's not doing anything. It should move and bring it back, and it doesn't do a thing. So I think this one, the control loop, is broken. So once again, it's an intimidating instrument, but since I have such a good signal from the tube, I can ignore pretty much everything. And what I have is the signal tube beam comes out of there and goes through the AC amplifier, and then it goes into a phase detector, so it figures out if you have a negative signal or a positive signal. It's a mixer. And then here you should get an air that's mostly DC. You amplify it, and then you slave the crystal oscillator to it. So the problem is either in the AC amplifier, the phase detector, the op amp, or the crystal oscillator. So I started over here, it's fine. So I'm going to move to the DC air. There's your test port for that. So we move to the next assembly, which is the phase detector. And one part just generates this 137 Hz signal. And then here's an active mixer. It's a phase detector, so it should tell me if I'm in phase or out of phase. And I should get the result out of here, and it should be mostly 0 when I'm well tuned, and it should go negative one way and positive the other way. So let's go see if that's true. So I'm going to remove myself from the test port of the amplifier and go on the, what is the output of this? Hold on a second. J1, phase detector output, not connected do anything. It's for your testing pleasure. Here we go. And see what we get on the scope. So we have our reference wobble and suppose. Huh. I see that I see no phase detection. So let's go back to 0. There you go. Why am I seeing nothing? And I'm tuning it and detuning it, and that thing should go positive and negative, and it does nothing. So basically my phase detector is not generating any error signal, and I know I'm going through the peak because, hey, I have 2 clocks, so why not use them to double check. Here, if I stop, I'm in tune, right? I'm on the cesium line. And if I go one direction, I'm on one side. If I go the other direction, I'm on the other side. So if I go back in the middle here, I should see my light extinguish right here. It did. So it knows it has second harmonic. If I go one direction, I'm tuned too much the other way, tuned too much that way. So I'm basically tuning it on the line by hand, but the phase detector is not working. That's my guess. And since we have the embarrassment of riches, I could actually take the phase detector out of this one, transport it into that one, and see if that solves my problem. Well, famous last words, I swapped my module, so this is the one that used to be in there, and this is the one that used to be in the other one. And I get the same exact problem. I don't get any change in the green line, average level, when I tune on either side. Okay, I've switched out. This is the signal out of the tube, and I am out of the resonance on one side, goes to the peak, out of resonance on the other side, and that doesn't do a thing. My green light should have moved up and down, and it doesn't. Well, maybe I'm onto something. I disconnected the input to the phase detector, which should be the same signal as the output of the tube that I showed you previously, but I had taken it from a test port over there, so it's supposed to be the same thing, but taken from a different place, and it's the yellow line, and there's nothing. I should have the same sinusoidal pattern that I had. It's supposed to be the exact same signal. So it seems to be a wiring issue. Wait a second, what's going on here? Here's phase detector A8. A bit complicated, but for now we are just concerned with the output, which we were measuring from test port J1 and stayed flat as a pancake. The input to the phase detector is the tube signal, which comes from amplifier A7. We were monitoring that one from the amplifier end before, and it looked great. But to be sure, I unplugged the other end of the cable, the yellow arrow here. We should see the tube signal arriving here. But no, nothing comes out of the coax. There is no input to our phase detector. No wonder we have no output either. But how is that possible? This coax comes from the amplifier assembly A7, and we had checked it before. That's the first thing we did. So let's go back there. Here it is. A bit complicated too, but we are just interested in the 137 Hz outputs. We can find the other end of our coax cable coming in port J4 and properly marked as going to the phase detector. And I had assumed the signal at J4 was okay because I had measured it using the empty test connector J6, which is there for this very purpose. And I'm not dreaming, J6 and J4 are connected to the same wire. What is coming out of J6 should also be coming out of J4. But it doesn't? What gives? Is my black wire broken inside the A7 amplifier? Or is the cable bad? One simple way to figure this out is to simply connect our coax to J6 instead of J4 and see if that fixes things. Okay, I moved the other end of the cable from the output part to the test part. It's buried way in there. These are disconnections here. I moved this cable. It was on the empty part here, and I move it over to here. And they're supposed to be the same thing, but apparently I recovered the signal. So let me reconnect the other end of the cable, which right now is on our scope, back to where it's supposed to be. Okay, I reconnected the other end of my cable to the input of the phase detector module, and now we see something. Yes, that's an error signal, and on one side of the resonance line it goes to plus, other side it goes to minus. Huh. Can I lock? Did I repair it? Into the operating position. Still didn't go on, but just might be the light that's burnt out. If I go on the control and control moves to correct, it does. I am now locked. So the light's not working, but I am locked and I should see it on the scope. So I have one bad light, and on the scope it is locked. Doesn't acknowledge that it's locked, so I still have a problem in the illumination of my green light, but we have recovered a cesium clock. Good. I think I know the reason why this is not lighting up. There is no bulb. Okay, let me get a bulb and see if that repairs it. CM327 28 volt bulb. Mid-jet flanged. Haha! There you go. It's a locked cesium clock that is working fine again. And also the nice thing with that clock is that, as you have noticed already, it has an actual clock and a divider. It gives you 1 pulse per second output. So that's an ideal clock to do a time drift measurement. And I took out the amplifier A7, and I don't get signal out of this plug over here, but I get the signal out of that plug over here, and they all should be in parallel. And they are. There's a big wire across all of them. And I measured it, it's connected. I look at the connector in the microscope, it's fine, so I don't know what happened. I'll resolder the connector just to make sure, in case the soldering was dry, but I don't see it either. And then maybe the plug was not put in correctly or something. I don't know. This is really weird.
A few moments later.
And then rejoicing was short-lived. It refailed. This time I have good beam current, but I have no second harmonic. I have no signal after the AC amplifier, so I think I lost it. It failed terminally. I don't know. Oh no, I can't believe it. It refailed right before my eyes. Is it something I did with the amplifier, or am I just cursed? Alright, so I'm suspecting the AC amplifier, and looking at the schematics, the AC amplifier is actually 2 amplifiers in one. There's the one that just gives you the beam current, that's this one, which is totally independent than the one that measures the AC. So it would make sense that I still measure beam current, but I have nothing going through this. And to test it's not that hard. It takes 18 volts, and I feed it a little sinusoidal signal at the input, and the output is my green, and I get absolutely nothing. And that's the output through here. So that's it gets just amplified, comes here, the second harmonic, because the signal is mostly second harmonic. And then it's a whole bunch of stages with filter that extract the first harmonic. And on the machine, I don't even get the second harmonic. And I confirm that here, that it doesn't go through. It's just a straightforward amplifier with 4 stages. So let's try to see where we lose it. I'm just going to go through the first transistor. So this is the input. Am I correct? It goes here. Yeah, so I have signal at the input right here. The output here, collector. Nothing. We don't even have anything at the end of the first stage. Let's look at the second stage, Q2. Nothing there. So we already lost that right in here. Let me check the transistor. Here's what that one is. It's an 1854-0023. And 1854-0023 is not one that's in the cross-reference, but I have it in my fish, which have been scanned and are available to everybody now on our archive.org. You just have to read through the fish and find it. It's a 30-volt transistor. It's not very fast, 15 megahertz, but you don't need to. It's low current, 1 milliamp, very high gain, 250 to 750. So it's a high gain and low noise, 4 dB noise figure transistor, which is what you would expect for a first stage of a sensitive amplifier. Okay, I'm surprised by the gain 250. Actually, looking just a couple lines up, this one is very similar, even a little bit better gain, noise figure of 3, even lower. So 2N5088 would be the possible equivalent, but I see what was something that would work for my collection. Well, I'm not actually sure what's going on, because if I test the transistor in circuit, it looks good. Yeah, it's a good 0.6 volt diode, another one, and it's high resistance in the other direction. So that tests like a good transistor in circuit. So maybe my theory about the bad transistor is taking water here. I'm still going to desolder it and check it on the on the curve tracer. And there it is, and as expected, it is a perfectly good transistor. So that's not what my problem is. Actually, I take it back. There's something not quite right about that first transistor. This is Q1, this is Q2, the same type. So right now I'm Q1, first glance it looks good, but then you look at Q2 and it has way more gain. Let me get it back in range here. Okay, so this is Q2, which is a good transistor, and when you calculate it out, it's about 400 gain. And now if I put the other one to scale, this one has only 80. And then if you look closely, there's something not quite right at the bottom. It's slow of the going. So so here I run it at 100 microamp in the base, and I'm getting 8 milliamps. But it's actually made in the circuit to run at 1 milliamp. So I am going to go way lower. I'm going to run it at a max of 10 microamps, and then there is nothing coming out. So the turn on is wrong. And then if you look at the other one, it's just perfectly happy. It has tons of gain. Okay, so here you see more the difference. This is Q2 now operating at the maximum of 10 microamps on the base and amplifying that to, what is it, 1, 2, 3, 4, amplifying that to 4 milliamps, so it's a gain of 400. And then the other transistor stays at 0, so something is not right with the first transistor. So let's replace it with something else. Alright, so I put a new Q1. It's an SS9014, and you can see it's a preamp low noise transistor made to run at 1 milliamp, so it's optimized at the same place. And I measured mine is gain 400, so it's a C, and the noise figures are 0.9, so that's going to be 4 times as good as the one we had there before, and that's the one that was good, so they are both about 400 gain. And see if that works better now. Okay. Here we go. We have amplification, a little bit too much actually, because I'm too high level, I guess. Yeah. All right. Okay, and it can get the signal down from the noise. Alright. And then we have low gain, high gain, that should work again. Alright, so it was a bad transistor. Whew, okay. Alright, and on this one, the evil HP people put this knob, which uses a Bristol wrench tool, which is some kind of a weird fluted version of an Allen wrench. So that's a pot to adjust the loop gain, which I suppose depends on the tube. Probably want to adjust that again. I'll put it back. So here go Bristol wrench, and then I marked out where it had to be. It had to be, sorry, over here. All right, the amplifier with the new transistor is back in, and on the other side, I have finally found what the problem with the connection was. It was the cable. It's still somewhere in there, unconnected, but I replaced it with a cable from another HP donor instrument. And all right, now the cesium is warming up, so we have to wait 15 minutes until this is done. All right, we're back. We have beam current, so hopefully the tube is still working. We have a ton of it actually. And dang, we still don't have second harmonic. What the heck? We should have a ton of... Oh, because modulation is off. And I have very weird signal at the output of my tube. Oh, no, that's correct. That's the correct behavior. Right, so I'm one side of the line, other side of the line, in phase, out of phase. So that's working fine. But why don't I have second harmonic? It should be able to lock on this. It is locked as we speak. I think if I leave it, it's going to go to 0. Yep. So it is locked as we speak. And I can check it over here. And we have the two cesiums that are crossing, so they are locked. Yeah, so it's locked at this point. Now it's in the servo loop. Ah! It's gone. Okay, so now it works. Do I have second harmonic all of a sudden? A little bit of it. We should have tons of second harmonic and we have very little. Oh wait, there's an adjustment for that. This one, hold on a second. It's my famous loop gain thing. There we go. Because I've changed the transistor, so the gain is okay. Now we're cooking. We have the correct reading in second harmonic. Okay, we're repaired. We're repaired. And if I turn the modulation off, it should 0. Yes. So this is not a spray signal, this is actually how it should work. Oof, okay, so we have our twice repaired cesium clock here that works, and that's the one that has the little clock. Actually, clock, why are you not working? Because I need to get you going. I need to get the divider going. Okay, so now we have clock, and we are locked, and we found our bad cable and our bad transistor, and we readjusted the loop. Okay, so we're back at it with our repaired clock and the other atomic clock, and you can see that Einstein is smiling because the result is much better. It's kind of a nice continuous deviation between the two clocks, which is okay. I can tune the clock. I haven't done the Z-man on that one, and then I can further align them so they don't deviate from each other, as long as it stays constant. If it starts to have hiccups, then I can't. Much better than the other clock, which I think unfortunately its tube is on its last leg and wouldn't work for a long-term experiment like we want to try. So let me try to do the Z-man alignment on that clock and redo an experiment and see if we can tune them on top of each other and have a kind of an average of 0 deviation.
After Z-man alignment, degaussing, C-field adjustment, etc., etc.
Alright, it's getting better and better. This is now, what is it, a 24-hour run, a little bit more, 30-hour run. And with the current C-field adjustment, I am now at a pretty continuous 0.3 nanosecond per hour about. So I'll give it a crank, maybe just one graduation in the other directions. Degauss it one more and then we should be good. And that's probably the best we're going to achieve with those two clocks. So I'll give it one more click. We're now at 482, and so far it's staying rather flat. We are a couple hours in, and it still tells me 0, 0. We'll let it run for a while.
The following day.
Alright, we have completed another 24 hours of our 7th run here, and we end up with a fairly clean trace and minus 6 nanoseconds in 24 hours, which is probably as good as we're going to get. So one graduation I'm plus 6, on the other graduation I'm minus 6, so I'm half a graduation away. But I'm never going to be able to zero it. We'll just have to measure what it is and use it in the final calculation to make Einstein happy. Alright, this is much better than last time. We have two clocks running within a few nanoseconds of each other. Still, this is pretty close to the time dilation we are trying to measure, so I am starting to understand why the original experiment needed so many clocks to average them out. Fear not, we have more to repair. See you in the next episode.